Hello. Okay. All right. Good morning, everyone. So I have shared the attendance form. I'll reshare the attendance form again. Those who have missed the form. So this is the attendance form. Kindly mark your attendance supplement. So let us start our discussion, remaining discussion today. And today we'll finish our discussion with linear regression. That is, our linear regression algorithm will be over today. And from the next lecture onwards, we'll start with another algorithm. We'll start with the classification algorithm, that is decision tree. So today we'll finish the discussion with linear regression. So let me share the screen now. So my screen is visible. Okay. Okay. So far our discussion in the case of linear regression was we discussed about the hypothesis function of linear regression. We discussed the hypothesis function for univariate linear regression, right? Univariate linear regression and multivariate linear regression, that is more number of features, right? Then we discussed the cost function of linear regression. The convexity of cost function of linear regression. Okay, and why it is convex, that we tried to understand. Then we discussed about gradient descent algorithm. Okay, gradient descent algorithm in case of linear regression. Gradient descent algorithm, the main idea behind gradient descent algorithm was to minimize the loss, minimize the loss. Okay, find theta 0 and theta 1, which are the parameters in our linear regression algorithm, such that the loss is minimum. Okay, the loss is minimum, and it is an iterative algorithm. So we'll start with an initial value of theta 0 and theta 1. Initial value of theta 0 and theta 1, and then we keep on iterating till we get minimum loss, that is global minimum, right? Fine. So we discussed up to this. Then we started our discussion in overfitting in case of linear regression. Okay, overfitting in case of linear regression. So we already discussed, when I discussed this particular slide, if you recall, when I discussed this particular slide, I stated that the fourth graph in this, which is a 9-degree function, is an overfitting function because it is fitting the data very well. So if you have any new data set, it will not give you proper output. So overfitting actually means it is performing well in training data set. In training data set, it is performing well, but in case of testing data set, it is not performing well. That is the case of overfitting. So today we are going to study one of the methods, some of the methods that you can deal with overfitting, methods to deal with overfitting. So there are some other methods too, such as you can decrease the number of features. Okay, for example, let us start our discussion in overfitting. For example, if you have too many features but too less data, only 2 or 3 data set is present, then there is a possibility that overfitting can occur. So in that case, one can do is reduce the number of features. That is one of the methods. But today we are going to see one of the method of to reduce the overfitting is regularization. If you see the definition of regularization, then regularization is a method which is used to reduce the complexity of function. Okay, reduce the complexity of function. That is the main idea of regularization. So what does regularization do is, for example, in this particular graph, if you see, this is a 9-degree polynomial. Or if you have a polynomial of this form, theta 0, you have a hypothesis function of this form, theta 0 plus theta 1x plus theta 2x square plus theta 3x cube, and theta 3x cube and theta 4x4. Now, Suppose your linear regression algorithm, your best fit line is something like this. Up to this is your best fit line. And if you have certain other features, then it is possible that your fitting line, that is the regression line that you are generating through this complex function, is something like this, which is not fitting your data very well, which is fitting your data too well, fitting too well, but it is not performing well on testing data. So what is the idea behind regularization is, you are trying to make the function less complex. So if I make the function less complex, that is, I reduce the value of theta3, the parameter value of theta3 and theta4, such that they are reduced to 0 or very minimum value, then it is possible that my function will be less complex. Yes or no? Are you getting? What will happen? So regularization is the idea to reduce the complexity of function. So we are trying to reduce the value of these parameters, theta3 and theta4, such that our function will become less complex. Okay? So this is the main idea behind regularization. So today we are going to see two types of regularization in the case of linear regression. One is rich and another is lasso. These are the two forms of regularization that we have in our syllabus for linear regression, right? Okay. So let us start our discussion now. So let me discuss with the PPT. Okay. So overfitting. So here you can see the first slide. In this particular slide, the first graph that is present is a case of underfitting, because it is not fitting the data, training data very well, and it will not perform well in the case of test data as well. Next graph is just right graph, that it is fitting the data properly, and it will perform well in training as well as testing. And the last one is, it is fitting the data too well, that is, it is giving overfitting. Underfitting can also be known as high bias, and overfitting can also be known as high variance. Why high bias? High bias means for any sort of data, any distribution of data, if your data is distributed in any form, this model will have a bias, that is, it will generate only one type of line for all the form of data. So this is a biased line. Okay, so this is also known as high bias. Underfitting is also known as high bias, and while overfitting is also known as high variance, where it is giving different values for test data. It is giving very good output for test training data, but when you are performing the same on the test data, it is not giving very well output. Okay. Now next. So we are utilizing, addressing the overfitting, the ways are to reduce the number of features. And then the next method that we are going to discuss in the case of linear regression is regularization, which is keep all the features but reduce the magnitude or values of the parameters theta j. And when we have a lot of features, it will, each of which contributes a bit to predicting y. This can be helpful in that case, right? Okay. So now I also discussed this intuition. So now what will be the updated? So what is the ridge? First of all, let us discuss the ridge regularization in the case of regularization. Up to this, everyone is clear why we are using regularization and what is the idea behind regularization? Everyone is clear with this? So shall we proceed with the first regularization form? Okay. Yes. So today, first regularization form, in this we are adding a regularization term in the loss function. So our loss function was something like this: y minus y hat, which is your output hypothesis function h of x, plus sigma the whole square, I is equals to 1 to n theta j the whole square into lambda. So what is lambda? Lambda is the regularization parameter. Okay, lambda is the regularization parameter, and in case of ridge regularization, we are adding the sum of the squares of all the parameters that are present in your that are in your particular this hypothesis function. So if your hypothesis function is theta 0 plus theta 1 x plus theta 2 x square plus theta 3 x cube, then we are actually, in this case, we are eliminating the bias term. This is known as the bias term. We are not adding any. This is an intercept. If you see, this is an intercept. Okay, we are adding only. Is ridge regularization more suitable for underfitting? I think No, maybe. I'm not aware of this. This is more, in case of overfitting, it is more helpful in case of ridge regularization. It is more helpful in case of, no, no, I'll come to this. It is more helpful in case of overfitting because what we are trying to do, we are reducing the loss. Okay, we are reducing the loss. So more is the value of lambda, more is the value of lambda. We'll try to reduce the value of parameters theta 0 and theta 1. But this won't be helpful in case of underfitting. There is a possibility that what can happen is, if you are increasing the value of lambda too high, then ultimately our idea is to reduce the cost function. That is our idea. So what will happen is theta 0 and theta 1 will be much less. So there is a possibility of underfitting in case of ridge regularization. If you increase the value of lambda too high, there is a possibility of underfitting. That is there. Okay, is that clear, Janet? Okay, now, so I was at this point. So we are eliminating the intercept term. What we are adding is, we are adding the slope term. We are adding all the slope terms. Okay, what are the slope terms? Okay, so our hypothesis h of x was theta 0 plus theta 1 x. Okay, this was our hypothesis in the case of univariate linear regression. Okay, this was our hypothesis function in univariate linear regression, and I had discussed that theta 0 is known as the intercept and theta 1 is known as your slope, right? That was your slope. So what we are adding in the case of ridge regularization, what we are doing is, we are adding in the loss, we are adding the main loss function that we had plus lambda into sum of all slopes, square of all the slopes that we have. Okay, that is what we are doing in the case of ridge regularization. Okay, now let us see through a graph. So what will happen is, the more the value of lambda, the more we will try to reduce the loss. Main idea behind this is, we are reducing the value of parameters. Okay, we are trying to reduce the value of parameters that we have, so that our function ultimately becomes less complex. Okay, that is what we are trying to do. Now we do not know which parameters to reduce. We have multiple parameters, theta 1, theta 2, theta 3, and so on. But we do not know which parameters to reduce. That's why we'll add all the parameters. And in ridge regularization, what we'll do, we'll try to reduce the values of this parameter. But it won't be equals to 0. It will just reduce to minimum value. Okay. And ultimately, it will make your function less complex. Okay. So what will happen? So suppose you have certain data set like this, certain graph like this, and you have two data points. These are the two data points that you have. This is the training data that you have. And this is the line, the regression line that is generated, that is passing through your data points. Okay, this is passing through your data points. So this is the case of overfitting, where it is fitting the data too well. Now what we are trying to do is, we are adding the slope square in your loss function with lambda, MSE loss plus lambda into slope square. So if you reduce the value of parameter theta 0 and theta 1, so your slope will ultimately reduce. So you will get less steep line. Yes or no? Yes? Yes? So ultimately, for example, if your data set was something like this, so again, let's see. So suppose your points are something like this. Okay, these were your points, and this was the line that was passing through the points. Okay, which was very steep, or consider this is less steep actually. Consider these are your points. Okay, so this is the data point line that is passing. This is the regression line that you have generated, which is actually overfitting, and these are your test data. These are your test data. So obviously, the distance of this test data from the actual regression line is very high. So your the MSE loss function will be very high. MSE loss value will be very high. So ultimately, what we are trying to do, our loss function will be MSE loss plus the lambda into slope square. So if we are trying to reduce the slope, which is theta 1, if we are trying to reduce the slope, ultimately your line will be less steep. So it is possible that you will end up in the line something like this. in which your loss will be minimum and your theta values will be minimum. But if you increase, now up to this is clear to everyone? What we are trying to do in case of regression, and the equation is clear? Up to this everyone is clear? Okay. What about others? Okay. Now, so lambda is your regularization parameter. Okay. So now we have observed that this is the in ridge regularization we are adding the value of slope square. So your loss is actually MSC loss plus lambda into slope square. Okay. This is what your MSC loss. This is what your final updated loss function is in the case of ridge. Now, if I increase, now suppose, let us take different values of lambda. So if lambda value is 0, then what will happen? If lambda value is 0, yes, same as normal. So overfitting will exist. Now, what will happen if lambda is too high? Okay, what will happen in the case if lambda is too high? Suppose it is close to infinity. Then what will happen? High loss, yes, high loss. There will be high loss every time because if the lambda value is too high, then as you I just now we discussed that we are reducing the slope value, then it is possible that if the lambda value is too high, then the theta values, that is the slope values, will reduce to 0. Okay, will reduce to 0, and in that case there will be underfitting. Okay, so your regression line will result into an underfitting case in case of lambda value too high. Okay, so up to this is clear. Both the conditions, both the cases in case of lambda and ridge regularization. Is everyone clear with this? Up to this? So shall we proceed with the next part? Yes, how to decide lambda? Yes, coming to that. Yes, yes. So we have to choose lambda. So that is one. I will also share one of the program that I have performed, that I have taken, in which we have found out the optimal value of lambda using cross validation. Okay, cross validation is one of the methods through which you can find optimal value of lambda. So ultimately, through what you can choose is you can choose different value of lambda from 0 to 10. Maybe whenever you are performing a program, a learning parameter. Yes, 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 right. So we have. Let me share that presentation. Wait a minute. Let me share that so that you will get an idea that how to choose the value of lambda. A minute. So here, let us see, just an observation. I wanted to discuss it at the end, but let us discuss here. So for example, in this particular program, we have a grid search CV, which is actually an method, which is actually a library that is present in scikit-learn. Okay, which is actually present in scikit-learn, through which you can find the optimal value of lambda. So in in theoretical part, we actually call this as cross-validation method, where we choose different values of lambda and you observe the loss, and whichever optimal value, whichever feels that optimal value of lambda, whichever gives you minimum loss, that is the one which you will choose as an optimal value of lambda. That is what we do. Okay. Yes, yes, right. Lambda minus alpha into loss. Okay, wait a minute. What are you trying to say? Lambda is equal to? Okay, updating the value of lambda, that is what you're trying to say, right? Okay, yes, yes. Okay. Yes, we are trying to update, we are trying to find the value of loss that is minimum. for which lambda we are trying to find out whichever loss. So here we have a function. For example, if you see grid search CV and we are passing negative mean square error. So actually what happens in grid search CV, it is trying to find maximum value. So we are trying to find negative mean square. That is why we are passing negative mean square. And we are trying to find the optimal value of lambda, whichever gives minimum loss. That is what we'll be choosing. So in short, cross validation, which is an method where will be a cross validation method, training and testing, that all discussed, right? If you recall. So this is one of the methods to find optimal value of lambda. Okay, is that clear? Janil, is the doubt clear? Okay. What about others? So shall we discuss the another form? Okay. So we discussed ridge. We can also call this ridge regression. We discussed ridge regression. In the case of ridge regression, we added slope square. Okay. But in case of lasso, what we'll be doing is, in the case of lasso regression, we'll be adding the absolute value of slope. We'll be adding the absolute values of slope in the loss. So your loss value will be MSC loss plus lambda into slope, the absolute values of slope. That is what we'll be doing in the case of lasso. So the idea remains the same in case of ridge and lasso, that you are trying to minimize the value of slope, minimize the slope values, so as to find a function which is less complex. Okay, the idea remains the same. Now we have an observation here that lasso regression is mainly used for feature selection. So lasso regression can be used in the case of feature selection. And how it will be used, that will come to that point now. So everyone is clear? The only update in case of ridge other than in case of lasso is, we are actually adding the sum of slope. That is absolute values of slope. That is what we are adding in the loss function. Okay, that is the only change in case of lasso regression. Now we'll discuss some other points in relation to ridge and lasso. So this is clear to everyone? Yes. Okay. So now, as I discussed, so now, so your loss function is, suppose I am considering your hypothesis function is equals to x into theta. Okay, this is for mathematical convenience, I am considering this as your loss function. Sorry, hypothesis function. This is your hypothesis function. Okay. Now, suppose consider what is your loss function in that case. Loss function will be y minus x into theta, the whole square, plus lambda into theta square. Okay, this is your loss function in case of ridge regularization. Yes or no? Now, if you want to choose an optimal value of theta, you want to minimize the theta. Minimize theta. What is the method that you can use? A method that you can utilize to reduce the value of theta, to find the minimum value of theta. What is the method that you can use? Find derivative when equal to 0? Yes or no? Okay. So now let us find the derivative of this. So what will be the derivative of this? Y minus x theta, the whole square, plus lambda into theta square. This is a loss function, and I am performing the partial derivative with respect to theta. Okay. So partial derivative with respect to theta will be okay. Yes or no? So this will be something like 2xy minus 2xy plus 2x theta plus 2 lambda theta, right? So the value of lambda is, sorry, the value of theta is 2xy, sorry, this is x square, upon 2x square plus lambda, 2 lambda. So I can ultimately say that theta value is equals to xy upon x square plus lambda. Okay? Yes or no? For ridge regression. This is clear to everyone. I hope that partial derivation part is clear to everyone. Yes or no? Yes. So now, if you see, whatever value of lambda you choose, okay, lambda you choose, if in case, if you want to make the parameter value here equal to 0, you need to have xy value equal to 0. Yes or no? In order to make the theta value equal to 0, the only condition that can make the value of theta equals to 0 is if xy is equals to 0. Yes or yes, is that is clear? So in case of ridge regression, we can say that in ridge regression, the value of, or yes, lambda equal to infinite, but we won't be choosing lambda equals to infinite in most cases. We'll be choosing lambda value to be an optimal value, right? Even if lambda value is very high, which is close to 0, there is a possibility that the value will be some 0.0000 something, but it won't be equal to 0. Yes? Yes or no? Yes. So we can say in case of ridge regression, in case of ridge regularization, your value of theta, we are trying to perform the, we are trying to reduce the value of parameters, and the only thing that will happen in case of ridge regularization will be, it will be the value, the coefficient value will reduce or come close to 0, but it won't be equal to 0. Yes, theta value will not be equal to 0. We are just trying to make the function less complex in case of regularization, and it will help in that case, right? Now let us see the same in case of lasso regression. Just a minute. So if you, okay, okay, so that is clear in case of ridge. Now let us see for lasso. So for lasso, your loss function was MSE loss, that is y minus x theta, where x theta is my hypothesis function. Okay, hypothesis function. This I am considering, this is for mathematical convenience. I am not adding 1 upon 2m and all, just for our convenience for now. Plus lambda into theta. Okay, this is your equation. Now, can I perform the derivative of this function? Yes or no? Can I perform the derivation of this? Yes, can I? Yes, I can. But see, do you know the absolute value? Absolute value is a non-continuous function f of x is equal to absolute values of x is non-continuous. It's not a continuous function because it is not differentiable at x equal to 0. If you recall, what is the graph of what is the graph of absolute function? What is the graph of absolute function? Anyone can point out what is the graph of absolute function? Anyone? Graph of absolute function? Yes, V-shaped graph. Yes, right. It was a V-shaped graph, if you recall. Yes. And if you see, I'm not going into the depth of this mathematics right now, but if you check by yourself, this function is not, it's a discontinuous function because it is not differentiable at x equals to 0. But while you see for x square, it will be something like this. Wherever you can form a tangent to the function, that function will be continuous form. But here you cannot form a tangent, okay? You cannot draw a tangent to this particular function graph, okay? Up to this is clear? Now let us do the derivation now, okay? Now what we'll do, we'll take for theta value less than 0 and theta value greater than 0. Okay, we'll perform the derivation for theta value less than 0 and theta value greater than 0. So now can you, so the loss function will be y minus x theta, the whole square, plus lambda into absolute value of theta. Now we'll take two different types of values, that is we'll take for theta less than 0, we'll perform derivation with theta less than 0, and we'll perform derivation with theta greater than 0. So right now, can you perform this particular, and can you state me what will the value of theta in both the cases? In both the cases, what will be the value of theta? Anyone? I'm giving you 2 minutes to try. So try this particular and give me the values of theta for both the cases when theta is less than 0 and theta is greater than 0. Okay, done. Keval is done. Okay, what about others? Yes, those who are answering me, Shell, Janil, Rikin, what about you? Did you try this? Are you people trying this? Okay, yes. Okay, any one of you who are, can you state me what will be the loss value in case of, sorry, what will be the theta value in case of theta less than 0 and in case of theta greater than 0? Is any one of you? Yes, yes.
Ma'am, in case of theta less than 0, value is 2xy plus lambda divided by 2x square.
Plus lambda divided by x square. Okay, in
2x
case
square,
of,
2x square.
okay, 2x square. Right.
And in case
Now,
of greater than 0, 2xy minus lambda divided by 2x square.
okay, good. Right. So this is right. So, yes, Rikin is getting the same value. What about others? Yes, right. So now let us see our observation in this cases. Okay. So in case of theta greater than 0, your value for theta is 2xy minus lambda upon 2x square. And in case of theta less than 0, your value of theta is 2x square xy plus lambda equal upon 2x square. Okay. Now, if we see for case of theta greater than 0, theta greater than 0, so if we see for different values of 2xy, for example, I'm taking an example value 2xy equal to 100, lambda equals to 50, and x square is equals to 2 or 50. Let us take 2 in this case. So what will be the value of theta? It will be something 20. Let us take 25 as a value. What will be the value of theta? Will be 2? Yes or no? Yes. Yes. Now, if you increase the value of lambda, lambda increases. Now, if lambda increases, theta value will decrease. And when lambda will come equals to 2xy, whenever the lambda value will be equals to 2xy, theta value will be equals to 0. Yes or no? Hello? When lambda will come close, will be equals to 2xy, which is your features, will theta value will be equals to 0? Yes or no? Hello? Okay, yes. Okay. So what will happen that in case of theta less than 0, theta less than 0, this was your form of theta, 2xy minus lambda upon 2x square. In case of theta greater than 0, this was your condition. Sorry, am I writing this right? No. Theta less than 0. 2xy plus lambda upon 2x square. So there is a possibility that your theta value will be equals to 0 in case of Lasso regression. If you see, in case of Lasso regression, your theta value can be equals to 0. So Lasso regression is used for feature selection. Okay, so if you see, if your hypothesis function is something like this, h of x is equals to theta 0 plus theta 1 x plus theta 2 x square and so on. If theta 3 x cube and theta 4 x raised to 4. If theta 3 and theta 4 is equals to 0, then ultimately these features will not have any impact in model generation. Okay, so ultimately you are selecting the features that are important. For example, theta 0, theta 1 and theta 2. So your function is less complex and it is helping in feature selection. That is, only important features will be selected, rest of the features will be eliminated. Okay, is that clear? So this is the case. For example, in 2x square minus lambda, if lambda comes close to 2xy, okay, lambda is equals to increases, theta value will keep on decreasing. Okay, lambda keep on increases, theta value keeps on decreasing. So suppose the lambda value increases more than 2xy, what will happen? This theta value will be less than 0. So now this function, we cannot use this particular formula if theta value goes less than 0. Then we will come to this function. Okay, then again, the theta value here, let us take 2xy is equals to minus 100 or something like that, plus lambda is equals to 100 or more than 100, 150, let us take 50 upon 2. So first the theta value will decrease as the lambda keeps on increasing. And at the point, the theta value will be equals to 0. But after the theta value comes equals to 0, there is a possibility that the theta value will either decrease further or increase. You can take for different values and you can check. If you want to check, you can check. So in that case, we will stop at 0. We will stop at 0. That's why some of the values, some of the parameters values in case of lasso regression will have theta value will be equals to 0. Okay. Just a minute. There is an announcement in the classroom. Ma'am is making an announcement. So just for 2 minutes. Wait.
Hello, class, am I audible to you? Class, am I audible to you? Okay, tomorrow at 2:30, you will have a lecture of CN. Extra lecture of CN will be there. I will conduct that lecture tomorrow at 2:30. Is it clear? Tomorrow at 2:30, what is the schedule? You are free, right? Okay, so tomorrow at 2:30, extra lecture of CN will be there, conducted by me. Right? So on this same link, I will be available. Thank you, ma'am.
Okay, so we were discussing about lasso regression, and in case of lasso regression, I discussed that theta value can be equals to 0, right? So in this lasso regression can be used for feature selection purpose, right? And we also saw that why is that the case. So we saw that in case of lasso regression, we were using different values. You can try for different values of theta and 2xy, and you can see that in this observation, that for particular value, the theta value will keep on decreasing. Then after a point, that is after 0, there is a possibility that theta value can further decrease or increase. Hence, we will stop at theta equals to 0. So there is a possibility in case of lasso regression, but in case of ridge regression, the theta value will be never be equals to 0. Okay, since it is 2xy, in the case of ridge regression, if you saw the value of theta, it was 2xy upon x square plus lambda. Okay, sorry, x square plus lambda. So in this case, in order for theta to become 0, xy needs to be equals to 0. But which will not happen because lambda, because these are the feature value that we have, right? So mostly this will not be the case. That's why in the case of theta, in the case of ridge regression, the theta value will be never be equals to 0. But in case of lasso, your coefficient value can equate to 0. That's why it can be used in for feature selection purpose. So is everyone clear with this, both cases, ridge and lasso regression? Anyone having any doubt? Is everyone clear with this? Okay, yes, cable is clear. What about others? Yes. Okay, fine. So these are the two cases of regularization in case of linear regression. So here our discussion with linear regression ends. So we have so far discussed, this was the case for overfitting purpose, right? We'll be discussing only the cases of overfitting, that is we are trying to reduce overfitting in the case of regularization. So here our discussion ends. In the next lecture, that is from the Friday, we'll be starting with the classification algorithm, okay, classification, which is decision tree. So now, so everyone is clear with, so far what we have discussed, let us revise this just once so that we can start with the next discussion. So far in case of linear regression, we have discussed the hypothesis function. We have discussed about the loss function in case of linear regression, gradient descent, and dealing with overfitting in case of linear regression. Okay. And we discussed the two cases, that is ridge and lasso regression, and why one of this lasso regression is used for feature selection. So today I will share with you the PPT presentation of both linear regression and the classification introduction presentation that we discussed. That both I will share. So you study this, and in the next lecture we will discuss if you have any further doubts in the next. Yes. Just one confirmation that I want to make, that the lecture that Madam just announced is tomorrow. That is on Thursday. Okay. That is on Thursday, tomorrow at 2:30. So everyone is clear with that instruction, right? So your lecture is tomorrow at 2:30. Okay. Yes. Fine. So far everyone is clear with linear regression. Let us we'll go through and code work as well right now. So everyone is clear up to this. Any doubts or anything? Yes, I'll wait for 1 minute. If anybody is having any doubt, they can ask right now. So we'll discuss one of the codes also, so that you'll get a brief idea about lasso and ridge regression, right? Okay. So shall we start the further discussion? So everyone is clear with this? Okay. All right. So there is a code implementation that I am sharing right now with you for ridge and lasso regression. So we are, in case of ridge and lasso regression, we are utilizing the linear model that is present in scikit-learn, and we are utilizing grid search CD, which is a cross-validation function, which is utilizing cross-validation in order to find optimal value of lambda. So we discussed that in order to find optimal value of lambda, we are utilizing cross-validation will be utilizing to find optimal value of lambda. So you can see that here we are using this particular diabetes data set on which we'll be performing the implementation. And we are, in this particular, there are 10 features that are present in it. So these are the 10 features that are present in this particular data set. And we are dividing the data set into train and test using train test split. This we have already discussed in the lab also. If you recall that we use train test split to divide the data set into training and testing, right? And then we are using this pipeline function that is present in sklearn.pipeline in order to perform two of the operation in the pipeline, that two of the operation that we want to perform. That is, first we want to perform the scaling of data, right? Scaling of data, standard scaler is scaling of data. You know about scaling of data? We had discussed about this in the second lab, right? So everyone has performed the practicals. Did everyone try the practicals for the second lab? Yes or no? Hello? Okay, you are done with this? Okay. Okay. Yes, we'll, by this weekend, so everyone has created the GitHub repository as well. Okay, partially you have done. Right, fine. no issues. But keep the repository updated. That is, you have time till Saturday to upload it in your repository, and I'll ask you to share the link of your repository anytime. So by that time, it should be updated, right? So now we are using grid search CV in order to find optimal value of lambda. So here alpha actually means lambda here. So we are using for ranges 0.1 to 10. We are using for 0.1 to 10 with a step size of 0.1, and we are using a 5-fold cross validation. So what is k-fold cross validation? If you know, k-fold cross validation is something like this. For example, in case of 5-fold cross validation, we are dividing the data set into 5 parts. So one part will be used for testing purpose, and rest of the parts will be used for training purpose. Now this part which was used in testing purpose will be taken for training, and the next part will be used for testing. And each time you will be using this part, different parts for testing purpose. That is 5-fold, right? 10-fold means you are divide the data set into 10 parts. You will use one of the part into testing, and rest of the 9 parts into training. And then you will add this testing part in the training part, and take one of the training part into testing part. Okay, this you will do for 10 times. This is k-fold cross validation that we have. This is a method for cross validation that we have. Okay, I suppose this is clear, right? Yes? Okay. Yes. So here what we are doing is we are implementing this. So we are using negative square mean square, because I said that in grid search. If you are using, yes, your question is, just a minute, what is your question? If we have trained model on part 2 and then use the same model for training in next epoch, won't that be bad? No, we are not using, okay, in part 2. No, we are not using the trained model. If you are, that trained model we are not using on the next part. We are using the, for example, we may use linear regression as a model to train this particular data set. Okay, train this particular data set. But each time we'll be using different set of data to train the model. Okay. So for example, this will create certain accuracy. This will create another accuracy. For example, in other parts, what we'll be using this part in training, and the rest part in, for example, this part in testing, and the rest of the part in training. That is what we'll be using. We are not using the same model to train the other data set. Are you getting what I'm trying to say? Yeah. Yes, Jenna? Yes, 5 models will be generating. Yes, that's what we'll be doing. So we'll be passing, so each of the data will be passed once into testing. If you can see, there will be k minus, so each of the data will be passed into testing at least once. Still, I'll just check this once. Whatever your doubt is, I'll check this once and come back to you in the next lecture. Okay, for the further insight into this. Okay. All right. Fine. So what were we discussing? Yes. So we are finding the optimal value of alpha using grid search CV. So that is what we are utilizing to find the optimal values of alpha. So here alpha actually means lambda. So as you can see, the lambda value is 0.3 in case of ridge regularization that we are using. So here we have passed the model, I guess. Yes. Here in this grid search series, we are passing the model. So here we have used Lasso as a model. And you can see that in case of Lasso, we are getting an lambda value as 1.2 or something. And if we use the same alpha into our coefficients, our coefficient value, sum of the coefficient value will be equals to 0. In case of Lasso, if you can see, sum of the coefficient value will be equals to 0. So ultimately, these won't impact in your model anymore. But in case of ridge, if you see the output, the coefficient value will not be equals to 0. They will be minimum. The values will be minimum, but they won't equate to 0. That's why ridge regularization, Lasso can be used in case of feature selection. Okay. Okay. Is everyone clear with this? So now I'll share with you the PPTs, so that you can get a reference to this. And so we'll discuss the next part, that is classification algorithm. in the next lecture. Okay. So far, everyone is clear with this, all the discussion that we did today. Okay. Is everyone clear with this? Okay. Fine. What about others? All right. So now I'll stop sharing. And I'll update the PPT, upload the PPT by today evening, and study the PPT and study the references that are provided in the presentation for your understanding. And if you find any doubts, you can discuss. We can discuss in the next lecture. But in the next lecture, we'll be starting with our another topic, that is decision tree classifier. Okay. So now, right now, I'll be ending the meeting now. And nobody's having any doubt in the lab session, right? Any doubts in the lab session? Did you try for other the topics? So if anyone is having doubt, we can discuss if it is possible. All right, fine. I suppose that everyone has signed the Google form. All right. Yes.